Welcome, class. Today we're going to continue our discussion of Chapter 3 and look at concepts involving energy and these physical and chemical changes that we talked about last time when we discussed matter. So the first point to make here is that all of those physical and chemical changes that we talked about also involve changes in energy. So when we're thinking about changing matter, we're also going to have changes in energy involved in that process as well. So first of all, what is energy? Well, the definition in this book and most other books is a pretty broad, basic definition, and that is simply the capacity to do work. Now, what is work? Well, work is simply an action of a force over a distance or through a distance. So, for example, if I take a book and push it across the table, I am applying a force over a distance. So, there's work involved in me pushing that book from one spot to another. Or, so energy, the capacity to do work. Right? So when something has energy, it has the capacity to do work. So now, we're not going to really get involved with work in any kind of real meaningful way in this course, but we will deal with concepts of energy. So that's really what we want to focus on. So if we think about energy, one of the things that you may be aware of is that there are two big types of energy, two kinds of energy, and that is what we call kinetic energy or potential energy. And so the differences here are that kinetic energy is any form of energy that involves motion. And the two most important types of kinetic energy in chemistry are what we call thermal kinetic energy and electrical kinetic energy. Thermal kinetic energy involves the motion of atoms or molecules, and electrical energy is, the motion of electrons. Now, we're going to mostly deal with thermal energy beginning in this part. We will, at the very end of the course, deal a little bit with electrical energy. Now, then there is also what we call potential energy. So these are types of energy that a material has because of either its position or composition. So two big types here are gravitational energy, which is an energy of position, right? So the higher something is off the surface of the earth, right, the more gravitational potential energy it has. And the one that we'll focus on in this class is this idea of chemical potential energy. And this is a potential energy of composition. So the composition of something dictates how much chemical potential energy it has. So what atoms are there? How are those atoms connected? What are the shapes of those molecules that might be involved? Right? All of that go into determining the chemical potential energy of something. Now, one of the key ideas that we have to remember here is just like in a chemical change, right, we have conservation of matter, right? So when matter can either be created or stored, we also have conservation of energy. So energy is conserved during a change. Cannot be created or destroyed. So, conservation of energy. What it can do, though, is energy can move, right? It can change form, meaning it can change from a kinetic energy to a potential energy, or move from object to object or place to place. So we can't create or destroy energy, but that energy can move from one place to another, or from one object to another, or it can change from one form of energy to another form of energy. Now, we also, of course, if we're going to be dealing with quantities of energy, we have to think about the units that these quantities will be expressed in. The two most important units of energy are the calorie, or what we call the little c calorie, and the SI unit, which is actually the joule. Now we have a nice straightforward conversion factor to go from calories to joules. 1 calorie equals 4.184 joules. Now there are a couple other forms or units of energy that you may come across. The first one is the big C calorie. This is simply a shorthand name for a kilocalorie, and it's equal to 1,000 little calories or 1,000 normal calories. This is also sometimes known as a food calorie, right? So when calories are put on food labels, they are actually big C or kilocalories. And we have what's called the kilowatt hour, which is an electrical energy unit. And 1 kilowatt hour is 3.6 times 10 to the 6 joules, or 3.6 million joules. Right? And by definition, 1 calorie is the energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So it's the amount of energy that is necessary to raise the temperature of 1 gram by 1 degree. That's 1 calorie of energy, or 4.184 joules of energy. So let's do a quick sample problem in units conversion here. So we can continually get more and more practice on this idea of units conversions, dimensional analysis. So we want to convert 750 calories into joules. So of course we're going to start with what we know, 750 calories. Now we need a conversion factor, right? And so we saw that on the previous slide, that 1 calorie equals 4.184 joules. So now we write this. So we want to end up with joules, so that's going to go on the top. We had calories, so that's going to go on the bottom. So 4.184 joules, 1 calorie. If I do my math, I end up with, on the calculator, something like 3,138 joules. Now, we can't forget about significant figures. And so, if we go back to our original measurement, it has 2 significant figures. Now, because there's no decimal point here, notice that we only have 2 significant figures here, so that my answer can only have 2 significant figures. So that's the 3, the 1. The 3 tells me to round it or to leave it the same. So I end up with 3,100 joules. Now, we could leave it like this, right? But remember, we try to avoid numbers that have zeros at the end without a decimal place. And so, since these zeros are not significant, the best way to write this would be, again, scientific notation. So 3.1 times 10 to the, so I have to move it 1, 2, 3, and I'm moving it to the left, so it's going to be a positive number. So 3.1 times 10 to the third joules would be the best way to write this. So we talked previously about one of the most important forms of kinetic energy when we think about chemistry is thermal kinetic energy. Now, we can combine that with this concept of temperature, right? And temperature is how we measure the thermal energy of something. So temperature is the measure of the average kinetic energy or the average thermal energy of the atoms or molecules that make up that material. So remember, thermal energy is involved with the motion or the movement of the atoms and molecules. And so if we think about the average kinetic energy or the average motion of these atoms or molecules, that's what we're measuring in the temperature, right? So if some of you may be familiar with the idea that if something is hotter, that means the atoms or molecules are moving faster, right? They have more kinetic energy, right? So the higher the temperature, the higher the average kinetic energy of those atoms or molecules are. In other words, the faster that they're moving. So temperature is how we can quantify the thermal energy of a material. Now, that is not to be confused with a related topic, which is called heat. So while temperature is the actual thermal energy, right? It's the measure of how much thermal energy the material has. What heat is heat measures thermal energy transfer. So heat involves the movement of thermal energy due to temperature differences. So this is what happens when thermal energy moves from a hot object to a cold object, right? The amount of thermal energy that moves is called the heat, right? So when we talk about the heat of something, we're quantifying how much thermal energy is moving or transferring from one object to another due to temperature differences. And thermal energy always moves from high temperature to low temperature, right? So thermal energy will always move out of things that are hot into things that are colder, right? So for example, when I put a cold ice cube into a warm beverage, thermal energy will move from that warm beverage into the ice, causing the temperature of the ice to rise and melt, right? So heat is thermal energy transfer. Temperature is how much thermal energy a material has. So when we talk about temperature, we have three common scales that we can measure temperature in. We can measure it in Fahrenheit, in Celsius, or Kelvin. Now in science, we predominantly use Celsius and Kelvin, and that's what we will use most of the time. You may come across Fahrenheit temperature once in a while and be asked to change Fahrenheit temperature into Celsius or Kelvin, or vice versa, just to get used to working with these different scales. One other difference that we should point out is that the Kelvin scale is what we call an absolute scale, and that simply means that there are no negative numbers. So 0 on an absolute scale is the lowest possible value for that scale. So 0 Kelvin is the coldest possible temperature, or what we know as absolute 0. Now, let's compare the scales and see how are they the same and how are they different. So we'll start with Celsius and Kelvin, since these are the two most common. Now, the one really nice thing about them is that the units are exactly the same size. So a Celsius degree is exactly the same unit as a Kelvin, or the same size as a Kelvin. Now, note one big difference here is that the units on the Kelvin scale are called kelvins. There's no degrees, they're just called kelvins. And on the Celsius scale, they're called degrees Celsius. But the units are exactly the same size. So it's a fairly straightforward conversion back and forth. So the Kelvin temperature here is always going to be the Celsius temperature plus 273.15. So if we look at the two scales, so 0 on the Celsius scale would be equal to 273.15 Kelvin. So add 273.15 and you get to the Kelvin. So 100 Celsius, 375, 37.5. Now, this value comes from the fact that scientists have estimated, right? It's never been actually achieved, but been experimentally estimated that absolute zero will fall at minus 273.15 Celsius, which would correspond to 0 on the Kelvin scale, the absolute scale, and so this is where that 273.15 difference comes from, right? That the Kelvin temperature is always 273.15 higher than the degrees Celsius. So that's a pretty nice, straightforward conversion. Now, the original temperature scale was the Fahrenheit scale, and this is a much more complicated conversion, or a more complicated conversion, for the simple reason is that the units are different size. So, in the same span, so between the freezing and the boiling of water, while there is 100 Celsius units, there are 180 Fahrenheit units. And so the Fahrenheit units are much smaller, right? And so we have to compensate for that, where we have 100 of these, we have 180 Fahrenheit units. So there's a factor of 1.8 smaller than the Celsius unit. So we have to work that into account. And so there's also this difference that we have to account for. So it becomes a more complicated conversion, and you can see the formula here. If you know the Fahrenheit temperature, you are going to minus 32 divide by 1.8 to get to the Celsius temperature. And so you should be prepared to make these conversions. These are not necessarily conversion factors, again, that you need to memorize, but you need to know how to do them. So let's do a quick example. So if we have 150 degrees Celsius, and let's, for the purposes of this, I didn't put it here, but let's say we have a decimal point at the end of this number. So let's say that our temperature is 150 decimal degrees Celsius. So in other words, this 0 is significant, we're going to say. So let's first go from Celsius to Kelvin. So as we saw here, the Kelvin temperature is the Celsius temperature plus 273.15. So in this case, we have 150 degrees Celsius plus 273.15 gives me 423.15 Kelvin. And we do have to consider significant figures, right? So remember, we are adding here. So decimal places become our the way that we determine it, not number of significant figures. So here we go out to the ones place. Here we go out to the hundreds place. So we have to stop at the ones place. So if I look at my answer and I cut it off at the ones place, becomes 423 Kelvin would be my answer. So now let's go to the Fahrenheit. So let's remember from the previous slide that my conversion, right, is degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. So now I know the Celsius, but I want to get to the Fahrenheit. So we have to do a little bit of algebra here to think about this. So if I take my degrees Celsius and I multiply it by 1.8 times 1.8, that's going to equal degrees Fahrenheit minus 32. So if I want to get degrees Fahrenheit by itself, I'm going to add 32 to both sides to get rid of it. So I have degrees Celsius times 1.8 plus 32 equals my degrees Fahrenheit. So my degrees Fahrenheit here is going to equal my degrees Celsius, or 150 degrees Celsius times 1.8 plus 32 is going to give me 302 degrees Fahrenheit. And so since we're doing the multiplication and division, right? Again, we don't need to worry about significant figures here in terms of using the 1.8 and the 32, because these are part of the formula. These are going to be, we consider these exact numbers, right? These aren't going to affect our significant figures. So however many we have in our original answer, our original data point. So since we have 3 significant figures here, we're going to end up with 3 significant figures here. So 302 degrees Fahrenheit. All right, so a little bit about temperature and how we go between different temperature scales and what those different temperature scales mean. So now that we've talked about thermal energy and temperature, right, measuring that average thermal energy and different ways to express that, in our next installment, our next lecture, we're going to talk about that transfer of thermal energy, or the heat, and how to calculate heat once we understand what that means.